All right, so we continue with the next session, and then the next speaker, Florenc Demrozi, has his PhD and Master of Science in Computer Science and Engineering from the University of Verona in Italy. And Demrozi is currently Associate Professor in Medical Technology at the University of Stavanger. He focuses on research areas such as artificial intelligence of things, human activity recognition, and active and assisted living. And today he's going to talk about edge-based freezing of gait recognition in Parkinson's disease. So please.
Thank you, Tom. Thank you to all the organizers, Nora and Sale and US. Do you hear me? Do you hear me now? A little bit better? Good. Okay, so thank you for introduction. I will present today a little bit of a part of my research activity related to Parkinson's disease. I normally work with many other type of diseases and so on, but this is one of the core areas. This is research that I have been doing in the last 6 or 7 years with many international colleagues from, you see here, for example, Verona, my former university, Limerick in Ireland, Polytechnic of Turin, and Arizona State University. So I think everyone here knows what Parkinson is, but probably many of you don't know very specifically what are the symptoms of Parkinson's. You have two main categories of symptoms, motor symptoms and not motor symptoms, and the freezing of gait that we have in the title is one of the motor symptoms. Now, these motor and non-motor symptoms are influenced by environmental factors, both of them. Environmental factors like the daily living environment, okay, like the medication adherence, like social isolation, like diet, like sleeping disorders, and so on and so forth. To make an example of the environment and how the environment is going to affect the motor symptoms in this case, let's think about the home, which is where most of these symptoms take place. In the homes, we have what we call risky places, risky positions. For example, doorways, for example, narrowing of the space because of furniture. For example, change in the color of the floor, okay, because there's a carpet, for example, in there. These risky positions, they will trigger or they will increase the possibility of having this kind of motor symptoms. And in particular, they are strongly related to the freezing of gait. So what is the freezing of gait then? Freezing of gait is this motor symptom which is basically blocking the capability of a Parkinsonian to move forward. So they try to move forward, their feet are glued on the ground, their upper body moves, but they cannot actually move. The brain is telling to the feet, move forward, but the feet are not responding. So what happens in those cases? They start moving, they lose balance, and they fall down. And that means a lot of higher injuries. Okay? How can we mitigate the freezing of gait? Yeah, sure, medication, but after a few hours the medication will lose its power, and also after a long term of using the medication will become less and less effective. Or we can have visual, tactile, or audio stimulation. Just think about a military march that says 1, 2, 1, 2, 1, 2, and this is going to help them to concentrate on the specific movement, okay, and not get distracted by the environment, for example, or by other people talking to them. Okay, there are a lot of devices that you can use. For example, you can put lasers on your feet, and the laser will provide a visual stimulation, which will go and trigger or show you the Parkinsonian the next position where they need to put their feet, and then the other one, and then the other one. You can have a belt which shows where you need to put the feet, and so on and so forth. But you imagine going outside the house with this kind of things, how disturbing that can be. This is why we are working on better solutions with the inclusion of machine learning and AI. This is an example of a Parkinsonian. You see, we have recreated narrowing over there, so a narrow place. The Parkinsonian is going on, and then he stops there. He's freezed. He tries to move. You see his legs do this, but he cannot move forward. So he needs to try and try and try, and then hopefully he will go out from the context, and then again he has an obstacle that disturbs him, and again, they will block there. With stimulation, in this case, you see he has a board over here. We have there some accelerometers and gyroscopes. We are monitoring the motion pattern of this person, and we are trying to detect the pattern that is going to tell us that in the next 2 seconds, this person is going to go and enter in the freezing event. And when we recognize it, the board will start vibrating and stimulating this person with the same movement frequency, the steps frequency, and help him to go on and to concentrate on the movement part. Okay? So this is a very good case, meaning that this subject was very good. It was perfect. This is why you see this video, not many other videos. Okay? But this kind of research needs a lot of effort, in particular because the motion between all of us is very different from each of us, in particular also in this kind of disease, where it's very subjective and it can affect different people in different ways, different parts of the body in different ways. So first of all, we started with creating a good system to collect the data. So we created a body area network, which can include 12 nodes that you can put in the body, and you can collect a lot of type of data from different parts of the body and so on and so forth. And we tested that body area network and also in other cases like after stroke rehabilitation, Parkinson's disease, sports, and so on. And then we needed to collect the data with that body area network. As you see here, we needed to define where to put the nodes. Okay, then we needed to design a protocol for data collection. This protocol is going to trigger as much as possible and stress as much as possible Parkinsonians to have as much as possible freezing of gaits. And then we need to collect the video because we need the video to do the annotation of what is going and what the sensors are saying to us. Okay? Now I will just go and show this specific work in which we use an existing data set because it's not so easy to find many patients in this type of category of people. This data set is called the TDCS data set. It's one of the biggest in the literature by today. They have only one sensor. In this case, they were using only the accelerometer on the lower back. Okay, so they are going to monitor the motion of these people with one accelerometer. We had in there 71 people with Parkinson's disease. They had collected 15 hours of data, of which almost 4.7 hours were actually of freezing events, for a total of 1,100 and something freezing events. The durations of freezing events are quite variable. You see here, you can have, or most of the events are short. They go from 1 second to a few seconds, but you can also have 100 seconds of someone freezed who wants to move forward, and they cannot, as soon as you don't really help them somehow. Okay, so this is a very difficult task because it works very well with long time, so 10 seconds of data, perfect, but then you lose all the short ones, but we want to recognize very short events, like 1 minute, in 1 second, sorry. Okay? So what is the goal in addition to this is that we want to create a model which runs on a resource-constrained device, so a board or a smartwatch with a few megabytes or kilobytes of memory. For example, this one, we have only 1.5 megabytes of memory to store things and 256 kilobytes of RAM. So we want to create a model to run it there. So in this case, yeah, we had a processing pipeline. I will just skip this. But the goal is create a model which runs inside here. No need to connect to the cloud, no need to connect to any computer, and which needs to tell us is freezing or not, starting from accelerometer data of 1 or 2 seconds information. Okay, this is our network in this case. We have a 1D convolutional neural network. We have another layer of convolution layer. Then we have a multi-layer perceptron added to the last part of the network, and then we have the freezing or not freezing part. Everything starts with accelerometer data, in particular 1 second of accelerometer data, 2 seconds, 3 seconds, and so on and so forth. To test the approach, we use a dataset. From this dataset, we can use only part of it. Only 62 subjects were good enough for us. Okay, so we used 62 here from the 71. We divided these 62. We used 41 Parkinsonians who had actually freezing events, okay, to train our model. Of these, we used 21 for training, 10 for validation, and 10 for testing. And then we used the remaining 21 subjects as another secondary testing fold. In addition to that, we took another data set from another project with multiple sensors, but they had the same sensor in the same position, so we used only that one to test as a third fold our system. We got very good results. For sure, we went way better than the original work on the same data set, and that was the only work at that moment. Okay, so we achieved almost 10% of increase in our performances. But as I said, and this was on the computer, so on big computers, not big, but normal computers, the ones that you have in your table now. But we wanted to go on the edge. So we wanted to go on the small sensor over there. So then we applied pruning and optimization techniques to the model, and we had it represented as float 32 bits. And in this case, you see the model size is 47.2 kilobytes, which is lower than or smaller in size than a WhatsApp message that you send every day to say hello to your girlfriend or to your parents or to whoever. Okay? The inference time of the model was 2 milliseconds, which means I give you 1 second of acceleration data. The model will take only 2 milliseconds to say freezing or not freezing. Then we optimize the model more. We wanted to be much more and much better with this model, to be much smaller. We optimized it again, and we reduced it into integer 8 representation, and we had 37.8 kilobytes of memory used. Again, way smaller than the previous one. The accuracy, we lost only 0.7% in the accuracy compared to a computer. Okay? And we reduced also the inference time to 1 millisecond. Okay? So that was it. We compared it with other works, in this case, on the same target, so edge computing, fog detection on other data sets. And as you see here, we were the one with the best results, basically, the one with the best results also in memory, from the memory perspective, and we also tested our system with the highest number of subjects. Nice fact, or fun fact or not, this paper was submitted to this journal. We got 2 reviewers the first time. It was rejected. We resubmitted again. We got other 8 reviewers, okay, and then the paper was accepted. That's it from my side. I hope you enjoyed it, and it was interesting for you.
Thank you. Any questions to Florence?
Very quickly. So do you believe at some point we will not need to have a back sensor and put a wearable sensor on the watch to be able to do that?
I think the wearable sensor on the watch will not be enough. Because, as I said, it's a non-symmetric disease, so it also depends on the body part that is not going to affect most. But for sure, it can be something that you can do with 2 or 3 sensors. For example, here, for this specific symptom. But then the goal...
At the moment when you test this with 1 sensor in the back only, right?
Yeah, in one sense, in this case, 1 sensor in the back only. But again, you have only 90%. So you are still missing a lot of cases. So that can be a problem if you have something that is vibrating on your body, like as a false positive. So the goal is to go as much as possible up. So we have other works with multiple sensors, which are much more accurate, like 99 or 98. But again, you will have multiple sensors, which creates the wearability issues and so on and so forth. Thank you.
Great. Short question here.
Yeah, just false positives. What happens to the patients if it vibrates and they don't need it?
It distracts them. Or the risk is that it distracts them and then they will freeze. And because that will become an environmental factor to them. So it will become something like when someone calls them, they are walking, someone calls them, or they hear a noise, and that will distract them. So it has to be very well synchronized with the motion that they have. So that's the risk of having false positives.
Thank you. Thank you, Florence, again.